Intensity pattern of capital N slits, part C. Using the properties of the exponential function that e to the a times e to the b is e to the a plus b, and e to the a to the power n is e to na, show that the sum in part B can be written as this expression. Then using the relationship e to the iz equals cosine z plus I sine z, show that the real electric field at point P is given by this expression. The quantity in the first square brackets in this expression is the amplitude of the electric field at point P. So that's the amplitude. Okay, so let's start part C. The electric field at point P is equal to real part of summation from n equals 0 to capital N minus 1, E0, e to the I, kr minus omega t plus n phi, as we have shown in part B. And this can be also written as the real part summation n equals 0 to capital N minus 1, E0, e to the I, kr minus omega t multiplied with e to the I phi to the power n, e to the I n phi, which is e to the I phi to the power n. So we're using this in part C, the given property of the exponential. Okay, so that's going to become the real part of E0 e to the I kr minus omega t. So now this does not belong to the summation. Sum n equals 0 to capital N minus 1, e to the I phi to the power n. Right, because there is no n here on this part, so that doesn't belong to the summation. It's just a multiplication factor. So we're really summing over e to the I phi to the power n. And now let's call e to the I phi x. And note that the magnitude of x is less or equal to 1. Right. Now if I have x to the power n, summation from n equals 0 to capital N minus 1, x to the power n. N equals 0 gives me 1. N equals 1 gives me x squared all the way up to x to the power capital N minus 1. I will call the result of this summation a. And if I multiply a with x, I will obtain the following. Sum n equals 0 to capital N minus 1, x to the n plus 1. This will be n equals 0 will give me x here, x plus x squared plus x cubed plus all the way up to x to the power capital N. Capital N minus 1 plus 1 gives me capital N. This is x times a. So you can see here, if I subtract a from x times a, I obtain x to the capital N minus 1, right? Because all the other terms are the same in between, so these terms will cancel. I will have x to the capital N minus 1. So a times x minus 1 is x to the capital N minus 1. Therefore, I will obtain the result of this summation to be x to the capital N minus 1 divided by x minus 1. So what does that mean? Electric field at point P is then the real part of E0 e to the I kr minus omega t. Now I have performed the summation e to the I phi to the power n is e to the I capital N phi minus 1, x to the capital N divided by x minus 1, e to the I phi minus 1. All right, and now this can be written as the real part of E0 e to the I kr minus omega t, and I will take the top to e to the I n phi over 2 parentheses, e to the I capital N phi over 2, and bottom e to the I phi over 2 parentheses. So I will obtain e to the I capital N phi over 2 minus e to the minus I capital N phi over 2. You see, if you multiply this with e to the I n phi over 2, you would get e to the I n phi, and you would get 1. For the bottom, I have e to the I phi over 2 minus e to the minus I phi over 2. And this will give me the real part of E0 e to the I kr minus omega t plus capital N minus 1 phi over 2, because this is n minus 1, capital N minus 1 phi over 2. And then I have this factor here, e to the I capital N phi over 2 minus e to the minus I capital N phi over 2 over e to the I phi over 2 minus e to the minus I phi over 2. Okay, now the electric field at point P is equal to a real part of E0 e to the I kr minus omega t plus capital N minus 1 phi over 2. And now I will open up this expression here. E to the I capital N phi over 2 is cosine capital N phi over 2 plus I sine capital N phi over 2. And e to the minus I phi over 2 is minus cosine. So I have minus e to the minus I n phi over 2, cosine n phi over 2, but there's a minus sign here, and the minus I sine n phi over 2 becomes plus I sine n phi over 2 because of the minus sign up front. And at the bottom I have the similar situation, cosine phi over 2 plus I sine phi over 2 minus cosine phi over 2 plus I sine phi over 2. So you can see that these cosine terms will cancel. So this cosine and this cosine, this cosine and this cosine will cancel. And I will have electric field at point P is equal to real part of E0 e to the I kr minus omega t plus capital N minus 1 phi over 2. So on top, I'm left with 2I sine n phi over 2. So this will be 2I sine n phi over 2. And the bottom is 2I sine phi over 2. Two i's will cancel, you will notice. So I will obtain the electric field at point P is real part of E0 sine n phi over 2 sine n phi over 2 divided by sine phi over 2 cosine kr minus omega t plus n minus 1 pi over 2 plus the imaginary part. So I have opened this up, so I have the real part of this is here, and plus I have the imaginary part here, I times this. So real part of this quantity is my answer. So I can find the real part. Electric field at point P as a function of time is E0 times sine n phi over 2 divided by sine phi over 2 cosine kr minus omega t plus capital N minus 1 pi over 2. And I can see that this is the amplitude term here. Okay, so in this part I was asked to find, using this relationship, e to the a, e to the b is e to the a plus b, e to the a to the power n is e to the n a. The summation can be written in this form, and finally the electric field at point P is E0 sine n phi over 2 over sine phi over 2 multiplied with this cosine term. So in order to do that, what I did was start with the electric field at point P as the real part of e to the I kr minus omega t plus n phi times E0. I isolated the e to the I n phi term. I wrote it as e to the I phi to the power n. And what remains at the front is basically something that doesn't belong to the summation, so I can take it out. So the summation is on this term, and e to the I phi is something less or equal to 1 in magnitude. And by using this geometric series for n equals 0 to capital N minus 1 x to the n, I can substitute for this summation x to the capital N minus 1 over x minus 1, which is e to the I n phi minus 1 over e to the I phi minus 1. E to the I n phi is e to the I n phi over 2 multiplied with e to the I n phi over 2. 1 is e to the I n phi over 2 multiplied with e to the minus I n phi over 2. And the same trick applies to the bottom. So this term is basically capital N minus 1 e to the I capital N minus 1 phi over 2, which goes here. And if I open this up using the Euler relation, cosine plus I sine, this cosine terms will disappear, the two i's will cancel, and I will be left with sine n phi over 2 over sine phi over 2. If I take the real part of this answer, basically I find that this is going to be, so here this is the real part of the whole thing. The real part of this is basically, if you open up the exponential here, the cosine term plus I sine term, that's the cosine term. So E0 sine n phi over 2 over sine phi over 2 is the amplitude of this cosine function.